So we are starting first part of our discussion, structure and bonding. Structure and bonding. First part. Now, what is free radical? Free radical is a reactive intermediate, obviously. Reactive intermediate means if A is reactant, B is product, in between the species formed, those are called reactive intermediate. Those are called intermediate, and those intermediate where half-life or lifetime is very low, those are called reactive intermediate. And among these reactive intermediate, carbocation, carbanion, free radical, and so many things are there. So one thing is free radical. Now, there are two type of bond cleavage. AB bond can cleave in two way. It can cleave like this. That is heterolytic cleavage. That will generate A plus B minus. That means if there is heterolytic cleavage means this bond, this covalent bond is actually made up of two electrons shared by A and B, and both the electron is using by both A and B. Now these two electrons are from both A and B, but after this cleavage, the bond breaking, both the electrons are taken up by B. So both the bonding electron is taken by one atom. That is heterolytic cleavage. Heterolytic cleavage. So that will generate ions. That means a cation or anion, or carbocation or carbanion. If A and B are carbon, then carbocation or carbanion. But another way, A, B. If one electron is going one electron is moving towards B, one electron is moving towards A, then it's homolytic cleavage. Homolytic cleavage. And what will generate? A dot plus B dot. And it will generate actually this dot actually free radical. Free radical. Now, very interesting thing to notice that in a free radical, suppose C, H, 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 in this free radical, this electron, this is not an extra electron. This is the electron of the carbon itself. Because A and B, when both were separate entity, when A and B were separate, then A has given one electron, B has given one electron. Then this bond has formed. Now, assume in such a way that they are taking back their electron. So this electron was with C only, right? So this is not an extra electron. When extra electron comes up, then we put a charge of negative on it. Okay, I hope you have understood it. Okay, now the question is, in what type of bond heterolytic cleavage will occur? In what type of bond homolytic cleavage will occur? The simple answer of the question is when delta chi means electronegativity difference between these two atoms. If delta chi is nearly about 0, that means electronegativity difference should be lower. So electronegativity should be very much similar, kind of. So in those systems, heterolytic cleavage will occur. If delta chi electronegativity difference is very high, then heterolytic cleavage will occur. And if they are nearly 0, then homolytic cleavage will occur. If delta chi is very high, that means electronegativity difference is very high. That means one will be very much electronegative, one will be less electronegative or electropositive. So here chi B is higher. Here chi B electronegativity of A is lower, because there is that much of electronegativity difference, and electronegativity difference is basically the driving force for the cleavage, that is heterolytic cleavage. But when there is no when there is no electronegativity difference or very minimal electronegativity difference, that will lead up to homolytic cleavage and thereby generation of free radical. I hope you have understood it. Now, first discovered free radical was, or first isolated free radical was this one, phenyl, phenyl, phenyl dot. And it was isolated in the form of, it was treated with Cl dot, generated in a particular reaction. Then it formed PH, 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 Cl. So this was the first reported free radical. Now we are reading structure and bonding, right? So there is, suppose let's take one free radical, carbon, hydrogen, A, B, C. Suppose how free radical is generated or what are the conditions we will study in the next part, because that is the part of formation part. So here, for example, this homolytic cleavage is occurring, and thereby I am getting A, B, C dot plus H dot. Both are free radical. but this is the free radical with radical on carbon. So we are basically reading organic chemistry, so we are much concerned with this species only. Now, to understand the property of this free radical, first, this is an odd electron system. Why odd electron system? In the valence shell of carbon, there is one electron, there is one electron, two electron, two electron, four electron, six electron, and another one, this electron, seven electron. It is odd electron species. That means seven electron species. Does it follow octet rule? No, it is octet deficient. It is octet deficient. Octet means 8 electron in the valence shell. So it is not less than 8 electrons. So octet deficient, CIENT. Okay. If it is odd electron species, then we can conclude that it is paramagnetic. Paramagnetic. And you can calculate magnetic moment also. Mu equal to, root over 4s into s plus 1. Root over 4s into s plus 1. And s means n by 2 number of unpaired electron by 2. Okay. Octet deficient systems are also called hypovalent. So we can call it as a hypovalent species. Hypovalent species. It is paramagnetic. So these are the basic structure in the Lewis dot model. These conclusions we have drawn from Lewis dot structure, Lewis dot model. We have studied so many model in chemical bonding to explain the nature of bonding. So these all the conclusions we have drawn from Lewis dot concept. Now we are going to draw conclusions from VSEPR concept. So from VSEPR theory, let's understand what VSEPR theory tells about the nature of that free radical. Free radical can be of two types. First one, type of CH3 type of, or CD3 type of, or CR3, R means alkyl group. This type of free radical are one kind of free radical. Second type of free radicals are like CX3 type of, CF3, CCl3, CBr3. These are another kind of free radical. This kind of free radical, these are planar. Carbon H, one above the plane, H, H. These systems are planar. This is planar. And tell me, what is the hybridization when a system is planar? Yes, this is sp2. This is one electron, that extra electron is there. So this is sp2 hybridization. Bond angle 120 degree. Is it so? It's a homework for you. Search what is bond angle for CH3 free radicals. Homework. Okay. Now, so CH3 dot, this system is planar. But this kind of system, CF3, let's see what is the problem in planar structure for this kind of system. CF, F, like this, F. Now, fluorine is very much electronegative than carbon. Then there will be very much negative pole. There will be very much negative pole, delta negative, delta negative, delta negative, delta negative. Now this lone pair, this single electron will undergo very much repulsion with this negative charge. All these three are actually equidistant, isn't it? This lone pair, this p orbital, and this bond is basically 90 degree distance. So all are in equal distance. So all will be facing similar kind of repulsion with that single electron. So what will happen? This bond will shift to lower side. So the resultant structure should be C like this, F, 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 F. So this is basically tetrahedral. The structure is tetrahedral and hybridization is sp3. Here sp2 planar, it is tetrahedral sp3. So this will be similar kind of CCl3 dot or CBr3 dot, all will be same, right? But there are different explanation also. There can be three explanation why CF3 is tetrahedral but CH3 is planar. So CH3 dot, that is planar, versus CF3 dot, that is tetrahedral. It can be explained in three ways. Different authors explain in a different way. First one, it can be explained through VSEPR theory. We know when terminal atom is more electronegative, then bond angle is less. Terminal atom has high electronegativity, then bond angle is less. If you have read anywhere VSEPR theory, then the conditions, the statements written there, you can correlate. That's why here bond angle is lower. Actually, the bond angle is 112 degree, but obviously this is lower. This is not a kind of sp2 hybridization. It is more or less a kind of similar. It is nearly equal to sp3 hybridization bond angle. Now, this is one explanation BSCPR theory. Second is percent S character or hybridization. If the structure is planar, then S character S character is 33%. If it is sp2 hybridization, if this structure is sp2, then S character is 33% because it is sp2 kind of planar structure. But if it is in tetrahedral form, then S character will be 25% or sp3, isn't it? Now, S character 33% means more electronegative orbital. That means orbitals will be more electronegative and thereby it will face more repulsion. More S character means more electronegative orbital. That means more repulsion. That means this orbital and this orbital electrons will show more repulsion. But here S character is less, so repulsion is less. These are two explanations, and another author is explaining this thing is in like there occurs some is saying that there is hyperconjugation like phenomenon. Hyperconjugation like phenomenon that occurs here, and you have no need to understand this in depth. So just understand these two explanations very well and just take it as a knowledge that there are another explanation also that is saying that it is hyperconjugation like phenomenon. Okay, hyperconjugation like phenomenon between whom? Between fluorine lone pair and sigma star of CF bond. So these are basically the structure and bonding part of free radical. Two homework for you. Find the stability order. First one I am writing CF3 dot is less stable than CH3 dot. Just search in Google or search in anywhere, ask your teacher, ask your friend. So what is the reason behind the stability order? It is homework for you to research about it. Why this order is like that. Then CF3 dot will be less stable than CH2F dot. Then CHF2. This is the stability order. This stability order is correctly written. Just what you have to analyze or what you have to self-study that why is it so. So do that yourself. Till now, have a nice day.